Hello everybody and welcome to the Chapter 9 lesson, your wireless metropolitan area networks. As always, we're going to cover what we hope to get out of our chapter here. Hopefully you'll be able to define wireless metropolitan area networks. You'll remember that we talked about metropolitan area networks and wide area networks in the 125 class, and now we're going to talk about the wireless metropolitan area network and like why they're needed in today's society, today's infrastructures. We're going to look at various land-based fixed wireless transmissions. We're going to compare wired versus wireless. We're going to take a look at broadband versus baseband. We're going to do free space optics and cover the differences in those and how they work with us. The 802.16 WIMAX standards will need to be covered. We're going to look at the features and security of the wireless metropolitan area networks. So, without further ado, we need to discuss, what we've covered so far. Now by now, you understand that the tremendous impact that wireless communications have had and will continue to have on the world around us. Wireless networks allow the user to be connected as they move around freely and without cables. Wireless networks allow users to be connected as you move about. However, wireless PANs and wireless LANs that you learned about so far restrict the mobile user to their homes and their offices and their campuses. Allows you to roam only a few feet to 100 feet from a source of the RF signal. Limits on the strength of the RF signal are mandated by the regulatory authorities, the FCC and so on. They're designed to prevent interference with these unlicensed bands of 2.4 gigahertz and 5. Users have to be subject to line of sight limitations also. So except for voice communications and data over cell networks, user mobility has remained largely confined to homes, offices, hotspots, and other wireless access, which, like your coffee shops and airports and other venues like that. In small towns, remote areas, the relatively small number of wireless network users might not make it, economically viable to implement hotspots and mobile access. In fact, in areas where there's low user density, the cost of installing cables to provide high-speed communication channels over long distances will typically prevent telephone companies or small ISPs from even offering high-speed internet access at all. Perfect example of that is where I live. Before I moved in here, we didn't even have broadband or cable on our street. Another example is the neighbor who lives behind me cannot get high-speed internet. He's still using old CenturyLink DSL to get online. So there had to be, there's got to be, other solutions for people like that who, where the big companies, they can't economically justify bringing connectivity out. In this chapter, we're going to learn about technologies and standards that allow wireless access to expand beyond a few hundred feet, to connect buildings several miles apart, or to provide internet connectivity across the entire city where the cabling infrastructure and extensive cellular network might not exist yet. We're going to look at and talk about coverage of infrared, base short distance, and medium distance technologies. And then we're going to finish up with standards for medium and long distance radio frequency based wireless MAN technologies. So we're talking MAN. If you remember from CNT 120 and 125, a MAN is a metropolitan area network. So you want to be thinking cities and large campuses. We learned that a wireless network that covers a large geographical area, such as an entire city or all its suburban areas, are wireless MANs, and they have typically two primary goals. These goals are to extend the reach of the existing wired network beyond a location without the expense of having to deploy high-speed copper or fiber optic cables. It's also to extend the user mobility throughout the metropolitan area. An important additional benefit of the wireless MAN is that it can provide high-speed connections, including internet, to areas not serviced by any other method of connectivity. Which takes us to something called the last mile of wired connection. Now, it's not literally a mile, just so everyone understands that. It's usually just the link between the end user and the internet service or the telephone company, but the term is sometimes used to refer to a connection to an entire community that was not previously serviced by telecommunication lines. Even today, most last mile connections are still based on some type of copper wiring, such as telephone cable, or even now we have fiber optic cables directly to the home users. In 2016, only about 25% of the homes in the United States were directly connected to fiber networks, and only a very small number of office buildings are wired for cable TV, in spite of its exceptional reliability for data communications. Fiber optics is slow and expensive to install. Most importantly, it's costly to maintain, especially in regions where the ground freezes and thaws every year, which can damage a lot of our buried cables. Here you can see an example of an overhead wired last mile connection. Today, home users in large metropolitan areas can take advantage of both DSL at up to a whopping 100 meg per second and cable TV connections of well over 150 meg per second. However, these types of connections are usually not available in your small and remote communities. Business users do have some other options beyond basic copper wiring. However, traditional wire technologies offer higher data rates and are much more largely available in your larger metropolitan areas. And they're typically quite expensive to lease a line, so costing several $1,000s per mile per month. Here you can see some of the traditional and historical connection options and speeds for homes, office buildings, and internet service providers to provide a kind of an idea of what we're going to be looking at for the remainder of this chapter. Like for long distance connections between cities and states, copper-based digital communications such as a T1 line required the signal be regenerated every 6,000 feet or 1.8 kilometers. In addition to the challenges of cable installation and maintenance, regenerating the signal requires electrical power at each repeater location. Maintenance cost for this type of connection is high, especially when the geography, the environmental conditions might be challenging. Since the 1980s, fiber optic technology has largely replaced all the technologies for connections between the major metropolitan centers, mainly because it's a higher capacity for carrying voice and data, and its maintenance requirements are becoming lower and lower, and it's more reliable than copper. However, the higher cost of the fiber medium itself, the actual fiber cable, and the in-ground installation will often preclude its use in remote and less populated areas. Now, most of the technologies used in wireless MANs and last mile wireless connections are based on microwave signals. but they also include infrared light. Microwaves are higher frequency waves that use the 3 to 30 gigahertz and the 30 to 300 gigahertz frequency ranges of the electromagnetic spectrum. Microwaves were introduced in the early 1950s by AT&T, and the technology brought about a whole new era in voice communications. Originally, the microwaves were used to transmit in more of a point-to-point fashion. But the conventional thinking in the early days was to use lower frequency. The high-powered approach was the only way in which microwaves could be used for communications. High-frequency microwave technology was ignored for many years, and the section of the RF spectrum between 27.5 and 29.5 gigahertz pretty much went unused. Microwave towers today are installed between 35 to 45 miles apart, and a microwave link operating at 4 gigahertz can carry about 1,800 voice calls at the same time. In comparison, a T1 can only carry 24 voice calls at the same time. Now, and the improvements in microwave technology have reduced the cost of the equipment, and they've made telephone data communication services available in many remote locations worldwide. Now, the current alternatives for a wireless MAN in the last mile connections include something called free space optics. Now, microwaves is an alternative to cellular data, which we're going to talk about in Chapter 10, and then also WIMAX. Now, a few legacy technologies, such as local multi-point distribution services and multi-channel multi-point distribution services, have been replaced, or they're, for the most part, being replaced by other technologies. Instead, we're going to talk about microwave links in this chapter, which, although not based on standards, have been and continue to be a very popular way of interconnecting cellular communication towers, buildings, and cities. Microwave is also used in a host of other permanent and temporary communication infrastructure setups. Using wireless as a last mile connection or to interconnect buildings is something called fixed wireless, because these are permanent setups fixed in one location, and they're not designed to support the mobile user. Fixed wireless networks have been used for several years for both voice and data communications, and in a lot of your what we call backhaul networks operated by telephone companies. A backhaul connection is defined as a company's internal infrastructure connection. So, for example, a telephone company backhaul network might be a connection from one central switching office to another. Cell towers along highways and areas where fiber connection is not available are usually interconnected using a wireless backhaul link. Now, these systems can be used to transmit the same type of data that's sent over a wired system. However, a point-to-point long-distance microwave link, such as those employed by your telephone carriers, use high-powered beams that are not always suitable or safe to use in a crowded city skyline. Now, if you remember, in Chapter 8, we learned that wireless LAN equipment, such as 802.11 wireless bridges, can be set up to connect two buildings, provided the installation doesn't interfere with other wireless links using the same unlicensed RF band. Installation of longer distance connections with this technology beyond the range of Wi-Fi, which is 375 feet, is possible, but can seldom achieve the high data rates required to interconnect in busy data networks. In addition to loss of speed, as the distance increases, the 802.11 standard is designed to support only a single repeater link, which means that a maximum of 3 bridges can be used between 2 destination points. Now, Another point that we need to talk about when designing wireless links is that there are two ways in which digital signals can be transmitted over a wireless medium. Now, the first one's called broadband. Now, many of you might know that you have a broadband connection in your home, but you might not understand until now. I did talk about it in the 120 class, but until now, what broadband really means. The first broadband here that we're going to talk about, it's multiple signals are simultaneously sent over the medium at different frequencies. And an example of broadband would be like your cable TV, in which you got multiple entertainment channels are sent on a single cable. But you also have your voice and you have data as well, all coming across that. When you pick a channel on your TV, the set-top box filters out all the other frequencies and just decodes and displays that single channel that you are trying to view. That's it. The second is baseband. Now, baseband treats the entire transmission medium as if it were just one channel and then transmits only one data signal at a time over a single frequency. That is what you have inside of your home network on Ethernet. Those examples illustrate the difference between broadband and baseband over a cable, but keep in mind that transmissions over an analog medium, such as an electromagnetic wave, can be sent as broadband or baseband. Purely digital signals can only be transmitted over a wire as baseband because mixing multiple voltage changes on a cable would create different bit patterns and basically just corrupt the data, given that there's no way to separate one signal from the other. However, if you modulate multiple digital paths over different carrier frequencies, they can be transmitted over any analog medium. The receiver can then separate each frequency using filters and then decode each of those digital signals. Also, it's important to note that there is no predefined frequency bandwidth separating baseband and broadband. So, for example, the wider the bandwidth, the more frequencies that are available to transmit separate channels of data using frequency division multiplexing. Alternatively, broadband transmissions can be made using time division multiplexing. Now, both methods can be considered broadband transmission. In comparison, a baseband transmission consists of only one data channel. Now, the data communications industry has developed a few different solutions for last mile connections over the past 30, 40 years. Some have proven too costly and were hard to justify. Others have proved to be less than totally reliable for implementation in all locations. Now, some RF-based solutions are proprietary, and some require the use of licensed frequency bands. Up until 2001, RF-based fixed broadband systems operated at frequencies with the modulation techniques that limited implementation to line of sight only. In addition, most fixed broadband systems could only send one site to another. In other words, they're set up point to point. As a comparison, in cell telephones, a single base station can communicate with several mobile devices simultaneously. Now, due to high cost of land-based communication lines from telephone and cable TV carriers, many companies have chosen to deploy their own building-to-building wireless connections. In here, we're going to be talking about and describing an infrared-based solution called free space optics. And later, we're going to learn about the IEEE 802.16 and WIMAX wireless technologies, which are used in fixed wireless networks and are also used for internet connectivity applications. Enhancements to the 802.16 standard also promise to help solve the challenges of user mobility and compete with DSL and cable TV. Next, I want to discuss free space optics. Now, it's an optical wireless point-to-point line-of-sight broadband tech. It was originally developed over 30 years ago by the military. It's become an excellent alternative to high-speed fiber optic cable for your short distances. Currently, it can transmit at speeds comparable to low-end fiber, reaching up to 1.25 gig per second at a 4-mile distance, which is crazy. And that's in full duplex mode. We're looking at speeds of hitting 10 gig per second. Now, the free space optics uses infrared light instead of a radio frequency. The light technology is similar to that used with a fiber optic cable system. The fiber optic cable contains a very thin strand of glass called the core. You learned about this in your 140 classes, for those of you who've taken that. It's typically only about as thick as a human hair. Typically going to be 50 micrometers for multi-mode, sometimes 62.5 if you have an older multi-mode fiber. And you're looking at 4 to 8 micrometers for single mode fiber. So that's as thin as a human hair. Instead of transmitting electrical signals, fiber uses light. Light source usually created by a laser or an LED flashes at one end of the cable and then is detected on the other end on the receiving end. Light travels at 186,000 miles per second. So fiber cables can transmit large amounts of data at obviously incredibly high speeds. In addition, the transmissions are immune to electromagnetic interference and cannot be easily intercepted without breaking the cable, which makes them, for the most part, relatively secure. Now, FSO is an alternative to fiber optic cables. So sometimes they'll call it fiberless optical. It does not use a medium like fiber optic to send and receive your signals. Instead, a low-powered invisible infrared beams carry the data. The beams, which do not harm the human eye, are generated by transceivers. Now, much like you can see here. Now, because FSO is line of sight, the transceivers are mounted in the middle or upper floors of an office building to provide a clear transmission path. Now, unlike other technologies that require the units to be located on an open roof, which sometimes requires leasing roof space from the building's owner, the FSO transceiver can even be mounted behind a window in an existing office. Now, if you remember that lower frequency portion of the electromagnetic spectrum is the area in which the RF and the EM waves travel, IR waves fall into the area above 300 gigahertz. So FSO uses the invisible light part of the spectrum region, and the only limitation on its use is that the radiated power must not exceed specific limits in order to avoid harming human eyes. The advantages include lower cost, speed of installation, transmission rate, and the security. Installations are significantly less than installing new fiber cables or even leasing from a local carrier. One recent project compared the cost of installing fiber to FSO to interconnect 3 buildings. The cost to install the fiber cables was about $400,000 compared to about $60,000 to install the free space optics. You put free space optics in a couple days, months, even years if you got to dig up streets and everything to put in your cabling. The transmission speed for FSO can be scaled to meet the user's needs. Typically now you can go anywhere from 10 meg to 1.25 gig, and we said we're going to be looking at up to 2 gig. Security, key advantage of FSO. Infrared transmissions cannot be easily intercepted and decoded as an RF transmission. Now, with every advantage, you're going to have a disadvantage. Some of these disadvantages to an FSO is atmospheric conditions. Obviously, will have an impact. Scintillation is the temporal and spatial variation of light intensity caused by atmospheric turbulence. Turbulence caused by wind and temperature variations can create pockets of air with rapidly changing densities. These air pockets can act like prisms and lenses that distort the FSO signal. Inclement weather is also going to be a threat. Rain and snow can distort a signal. Fog does the most damage to light-based transmissions. Fog is composed of extremely small particles of water that act like prisms, scattering and breaking up the beams of light. Now, the FSO can overcome the scintillation by sending the data in parallel streams from several separate laser transmitters. These transmitters are all mounted in the same transceiver, but are separated from one another in such a way that it's unlikely that while traveling between the transmitter and receiver, all the parallel beams will encounter the same pocket of turbulence, given that scintillation pockets are typically rather small. At least one of the beams will arrive at the target node with adequate strength to be properly received. This solution is called spatial diversity because it exploits multiple regions of airspace. An example of spatial density or spatial diversity is shown here with parallel light beams coming from an FSO transmitter. Dealing with fog, there are several potential solutions. One is to simply increase the transmit power of the signal. In regions of heavy and frequent fog, it may be necessary to choose FSO systems that transmit at the heaviest available frequency because these devices can also emit at the higher power levels. Several vendors also claim to customize their distance and product recommendations based on weather statistics for particular cities. Now, there are a whole bunch of different applications for free space optics. Some of the more common ones would be the last mile connection, where we use it for the high-speed links to connect the end users to the ISP. FSO devices are easily installed for LAN connections, making them a natural solution for interconnecting LAN segments that are housed in buildings separated by public streets or other obstacles. A backup for fiber optic, and also can be used to carry telephone traffic from antenna towers back to the facilities. Most of the experts are agree that the FSO holds a lot of potential for your fixed wireless connections. In spite of other technologies' advances, FSO has remained a stable player in wireless field today. So next is wireless links, and as we talked about at the beginning, microwave is a group of wireless technologies that, although not based on standards such as those from the IEEE, it is a common way of interconnecting buildings, cell towers, intercity telephone networks, and so on. Now, microwaves are essentially EM waves, but the microwave is not meant to imply that the wavelength is in the micrometer range. It is simply meant to suggest that the wavelength is smaller than the wavelength of a radio wave. AM broadcast radio stations are at the time operated and still do mostly in the 535 to 1605 kilohertz range, which have wavelengths varying from approximately 1839 feet to 613 feet, respectively. Microwaves have not been used to transmit telephone calls since the mid to late 1950s across North America, and can operate in the range of 300 to 300 megahertz, which have wavelengths ranging from 3.2 feet to roughly 0.00328 feet, or roughly a millimeter. Microwave transmitters today operate at a variety of frequency bands from the ISM at roughly 5.8 gigahertz all the way up to 80 gigahertz. Most microwave links installed by carriers today are point-to-point lines of sight, permanent links that typically operate in the 18 gigahertz licensed frequency band. It helps carriers to avoid the potential interference and ensure the reliability of their networks. Now, because of the lack of standardization and interoperability, testing, such as the ones conducted by the Wi-Fi Alliance, each carrier's link must use equipment from the same vendor. Data rates can change up to 2 gig for a single transmitter to 4 gig for aggregated transmitter setups. Say you're using 2 transmitters. And then they use between 256 and 1024 QAM, quad amplitude modulation, with parabolic dish antennas, which are highly directional and very high gain. Carrier links use the frequency division duplexing, FDD, transmitting on one frequency and receiving on another for a full duplex operation. And practically all microwave links in use today carry 100% of IP traffic. In the past, microwave transmitters were large and needed to be installed on the ground at the base of communication towers with what we call waveguides, regular cavity metal tubes that carry the transmitter signal from the ground to the antennas installed high up in the tower, with each copper antenna cable or waveguides. Now, the main issue was a signal loss between the transmitter and the antenna. Today, the transmitters are very compact and are installed on the towers right next to the antennas, which minimize or eliminates any signal loss, and some products are available with integrated dish antennas. So here you can see an example of a microwave transmitter. Some products are also available as a split architecture with data circuits installed at the bottom of the tower and the radio waves installed on the tower right next to the antenna. Now, many businesses use compact microwave equipment working in the unlicensed 60 and 80 gigahertz bands to deploy private high-speed links. So, like an example, a college campus wanted to interconnect 5 buildings, 2 of which were across a public street. The college originally leased fiber optic lines from the local utility, but because of the location, the optical lines ran from one side of the street to the downtown core and then back from the downtown core to the other side of the street. So the total length of the leased fiber line was approximately 5 miles, and the cost of the 1 gig link would be about $8,000 a month. But the college looked at the maximum data rates required to interconnect the buildings and decided to install 2 separate 66 meg links, one to each building across the street at a cost of about $60,000 to link the wired and Wi-Fi networks to 2 buildings. This meant that the cost of the wireless link was paid for in roughly 7 months when compared to leasing the optical lines. Temporary links, or we have microwave equipment currently available to support temporary installations. You would need these type of links, say, for sport venues, the Olympics, Pan American Games. These mobile links typically use the 5.8 gigahertz ISM band, and they create a small microwave cells that can be used to transmit multiple 100 to 200 meg non-line of sight to each of 3 other points, so it becomes a point to multi-point, or to a single point with an aggregate data rate of up to 600 meg per second. Now these links use smart antennas, beamforming, time division duplexing, and OFDM with subcarrier modulations of 128 and 256 QAM. Now it takes us to 802.16 WIMAX, which is an open standard broadband metropolitan area network technology that can work in either line of sight or non-line of sight, depending on the frequency you're using. And it's designed to support a whole variety of fixed or mobile digital communications. Now, the term WIMAX stands for Worldwide Interoperability for Microwave Access. The IEEE introduced 802.16 way back 20 years ago in 2000 with the goal of standardizing fixed broadband wireless connections as an alternative to wired access networks like fiber and cable TV and DSL. The 802.16 supports enhancements and extensions to the MAC protocol so that it's possible for a base station to communicate with another base station as well as directly with the subscriber stations, which can be either a laptop computer or a device that attaches to a LAN. FSO cannot support mobile communications because of its directional requirements. Now here, what you can see here, this is a WIMAX lab setup that includes 2 base station controllers on the top and 4 substations down there at the bottom. Each 2 substations in the graphic are connected to one of the base stations that are in the middle and the vertical there. The flat areas in the front of the substations are integrated antennas. So the SSs in the photo are normally installed on the outside wall of the house or building facing the antenna of the nearest base station. But for safety reasons, the lab equipment is interconnected using cables and attenuators instead of antennas because of the high power RF signals. Now, a group of manufacturers established something called the WIMAX Forum back in 2001 to promote the implementation of 802.16 by testing and certifying equipment for compatibility and interoperability. The 802.16 standard offers multiple RF interfaces depending on the frequencies used and associated regulations for different countries, but they are all based on common MAC protocols. Now, with data rates of up to 70 meg per second in the 2 to 11 gigahertz bands and up to 120 meg per second at short distances in the 10 to 66 gigahertz bands, WIMAX is suitable for backhaul business applications as well as last mile delivery applications. So it's actually capable of replacing a T1 and DSL and cable TV modems for your internet. WIMAX can support simultaneous voice, video, and data transmissions for quality of service. The convergence of voice, video, and data of IP networks is what the industry calls triple play. Now, WIMAX enables vendors to create many different types of products, including various configurations of base stations and customer premise equipment, which are the devices that installed at the office or the home. In addition to supporting point-to-point, multi-point applications, WIMAX can be deployed as a point-to-point network to provide broadband access to remote and rural areas. Now, manufacturers can design and build standards-based equipment that can be employed by wireless operators using licensed frequencies, but also by business users using both licensed and unlicensed frequencies. Compared to other technologies, the cost of WIMAX equipment is attractive. For example, the cost of a WIMAX customer premise equipment has dropped below $100. Some CP devices can support TV, video, so your telephone and your data. So it can handle the triple play. The WIMAX MAC layer includes features designed to make it easy for carriers to deploy the network. Once the BSSs are in place, and an end user can connect to a WIMAX network by simply taking the CPE device out of the box, placing the antenna near a window, or mounting it on an outside wall, facing the nearest BS, and then turning it on. In contrast to configuring a wireless or a Wi-Fi wireless gateway, for example, little or no configuration is required by the customer to install WIMAX. Now, the 802.16 covers a huge, wide range of functionality. It's got a number of variations that address specific applications. It defines the interface specification for fixed point to multi-point broadband wireless metropolitan area networks. The 2001 standard included a PHY layer spec for systems operating in the 10 to 66 gigahertz range. Formed the basis of all other standards in the family. In 2004, came out with a revised version that supports operating from the 2 to 11 gigahertz range. The 802.11.16e amendment to the standard, ratified way back in 2005, defined the specification for a mobile version of WIMAX. The 802.16m was an amendment for the by the WIMAX forum. Raises the data rate to 100 meg per second and makes it possible to combine MIMO, multiple frequency channels, and spatial multiplexing to achieve data rates of up to a gig per second. As with many of the technologies that we've talked about, the PHY and MAC layers are the only ones that change between different networking standards. WIMAX is unique in that, in addition to the PHY layer supporting multiple frequency bands, its PHY layer is able to adapt on the fly. The modulation techniques and access mechanisms can change dynamically from the BS to the SSs, as well as to other BSSs, depending on distance, the existence of any interference, or the requirements of the particular device itself. It has the ability to dynamically change. Now, unlike Ethernet, the MAC layer for WIMAX is connection-oriented and includes service-specific convergence sublayers that interface to the upper OSI layers. Now remember that in the OSI protocol model, only the transport layer is connection-oriented. The convergence sublayers of the MAC layer in WIMAX can map a particular service to a connection, which allows WIMAX to offer multiple simultaneous services through the same link and to carry mixed communication protocols such as IPv4 and IP version 6, Ethernet, VLANs, and others, all on the same link, on the same network. The MAC layer in WIMAX also includes a privacy sublayer that is used to secure the link. In the PHY layer, there are several variations of the layer in 802.16, determining which variation to use for a particular implementation. That'll depend on the frequency range and whether it's a point-to-point or point-to-multipoint. The first two are based on modulation of a single carrier signal. Now remember that when transmitting on a single frequency, all transmitters have to work in half duplex mode because they cannot transmit and receive at the same time. In this case, each transmission is divided into fixed duration frames that are 5 milliseconds long. Each frame is subdivided into one uplink subframe and one downlink sublink frame. And the BS transmits to the SSs during the downlink subframe, and the SS transmits to the BS during the uplink subframe. The PHY frames can be 0.5 milliseconds to 1 millisecond or 2 milliseconds long and are divided into a variable uplink subframe and downlink subframe. The subframes are divided into a series of slots, and because the uplink and downlink subframe is variable, the BS can allocate more time slots for the uplink or down as required. Now, a data transmission to or from a single device using multiple time slots is called a burst, and a burst can be a broadcast transmission from the BS to all SSs, and the transmission includes commands or network management information that is then sent prior to the transmission of the frame's data portion. The BS allocates time slots for specific SSs in both the downlink and the uplink frame. The amount of data contained in a burst depends on the number of and the length of the time slot, as well as on the modulation and coding scheme that's used in the particular burst. Now, WIMAX also allows the use of two different frequency channels, the FDD. The structure of the frame in FDD is similar to that of TDD, except that one frequency is used exclusively for downlink and the other frequency would be used exclusively for the uplink. WIMAX can support less extensive half-duplex equipment as well as full duplex stations simultaneously, using different frequencies on the same network and at the same time. When half-duplex transmitters are connected to an FDD network, the BS needs to make sure that it does not schedule time for those devices to transmit and receive. Simultaneously, given that these are half-duplex stations only. Access to the uplink direction from the SSs to the BS uses time division multiple access, in which one or more time slots are allocated to each SS depending on the requirements of the type of data being transmitted. In the 10 to 66 gigahertz licensed bands, the 802.16 in 2009 supports one transmission mode, wireless MAN SC or single carrier. It's used for fixed point-to-point connections using either TDD or FDD. Now, at these higher frequencies, line of sight to the transmitter and directional antennas are required. All other transmission modes in WIMAX are designed to work in the 2 to 11 gigahertz licensed or unlicensed bands. Now, the 802.11.16 standard also supports non-line of sight applications. Non-line of sight occurs when the transmitter antenna cannot be seen from the receiver's end, or vice versa, because of the geography of the area, or obstructions of buildings, trees, etc. It might be blocked by the Fresnel zone by more than 40%. Remember, the Fresnel zone was that kind of like an oval transmission that goes out because it narrows at each end. Outdoor tower mounted antennas for homes can be expensive to purchase and install, especially in areas subject to high winds or ice accumulation, and significant multipath distortion is likely to occur. Now, remember that when using directional antennas for inline of sight applications, multipath distortion can safely be ignored. However, in point-to-multipoint applications, the BS will typically use an omnidirectional antenna to support line of sight applications, the additional PHY layer functionality will be required. The introduction to WIMAX here, we discussed like the generic functionality because there are far too many options. We could actually write an entire book on WIMAX itself. The wireless MAN OFDM can be used for fixed, mobile, or mesh applications. It uses TDD or FDD in licensed band below 11 gigahertz. This mode divides the frequency band into a number of data subcarriers, pilot subcarriers, and null subcarriers to make it resistant to multipath problems. The radio does not transmit during null subcarriers, and null subcarriers are used as guard bands. Remember, guard bands are used to prevent the signals from kind of like blending to the other, over to the other signals. The OFDMA uses orthogonal frequency division multiple access. This technique is based on the OFDM that divides the available frequency channel into 1536 orthogonal data subcarriers, which allows for transmissions of frames to different destination devices and from different sources. These subcarriers are then grouped into subchannels, and each SS is allocated a subchannel, allowing multiple stations and the BS to communicate in a single transmission. Here again, the number of data subcarriers is dependent on the channel width. A third transmission mechanism, wireless high-speed metro area network, called wireless human. It's also based on OFDM. It's specifically designed for use in unlicensed 5 gigahertz U and II bands. In 802.16, the OFDMA is also scalable, meaning that the number of subcarriers allocated to an SS for the uplink can vary depending on the quality of service requirements, the signal quality, or the distance between the SS and the BS. However, to accommodate channel aggregation, which is multiple contiguous channels, in 802.16m, the number of UL and DL frames is fixed and asymmetric, meaning that there are more DL frames than UL frames. Another key characteristic of the 802.16 PHY is that it supports adaptive modulation. So in simple terms, it means that for each SS, the 802.16 can dynamically change the modulation, increasing or decreasing the data rate based on signal quality. In addition, in order to meet the regulatory requirements in different countries, as well as to optimize the use of the spectrum, the 802.16 standard allows transmitters to use frequency bandwidths of a minimum of 1.25 megahertz up to a maximum of 20 megahertz. Now, here you can see WIMAX specification nomenclature. Frequencies used, the applications, and duplexing alternatives are all listed in this table. Now, in 802.16, modulation and forward error correction, FEC, they're directly linked. In addition to the forward error correction, 802.16 uses automatic repeat requests, or ARQ, to ensure the reliability of the transmission. So in other words, sometimes it's necessary to resend the frame. 802.16 was designed to achieve a 99.999% reliability. Okay, something we call the 5 nines as a level of reliability. It's commonly referred to in the computer industry that way. The FEC improves the chances of receiving the data correctly and thus reduces the number of retransmissions, which increases the performance of the link. Now here you can see the types of modulation supported in 802.16 and the associated mandatory FEC coding that goes with it. Now the coding rates are listed here basically just for informational purposes. As we said before, a full explanation of the FCC is beyond this class. However, it is important to know the different FEC coding rates that are used for increasing the reliability of the transmission itself. Now, the ability of 802.16 to dynamically change modifications is also what also makes it possible for WIMAX to reduce latency and improve the quality of service. Remember, latency is the amount of time delay it takes for a packet to travel from its source to its destination, not back again, just the source to its destination. So here you can see an example of how WIMAX can use different modulations, and adaptive modulation allows or helps WIMAX use the channel bandwidth more efficiently. Now, the BS sends information to the SSs about which modulations it will use for a particular burst, okay, which is our signal being sent, and for a particular SS in the first few data frames at the beginning of the transmission. The SSs then will respond by sending information to the BS at the beginning of their assigned bursts. Now, the 802.16 defines certain profiles, which are sets of predefined parameters that can include the frequency channel, the bandwidth of the channel, and the tradition mode, whether it's going to be OFDM or OFDMA. Now, these profiles also help to reduce or eliminate the need for what we call truck rolls, which are support technician visits to the site, given that, they can be changed remotely if they can't be changed remotely. WIMAX also specifies basic profiles, point to multi-point or P2MP and point to point PTP, as well as an optional mesh networking profile. The WIMAX system profile is a combination of the basic profile and one of the transmission profiles, and it's preset on the equipment by the operator companies or the carriers before it's shipped out to the end user. The burst profile are negotiated between the BSs and the SSs for the allocation of time slots that are required in order for them to maintain quality of service. Now, the maximum distances achievable in WIMAX networks depend on the frequency band that's being used. Now, if you remember that the higher the frequency range, or the higher the frequency, the shorter the range of the signal at a given power setting. Conversely, the higher frequency signals allow for higher data rates. Now, in general, higher frequencies are used for metropolitan area line of sight, point-to-point applications at very high rates for carrier networks using licensed frequencies. Lower licensed frequencies below 11 gigahertz are typically used for private line-of-sight network connections of up to, say, 10 miles, as well as for long-distance links of up to 35 miles. Frequencies below 11 gigahertz are used for non-line-of-sight networks with a maximum range of up to 5 miles. WIMAX base stations and subscriber stations perform ranging or distance calculations based on signal quality. The process occurs when the subscriber station initially joins the network and then periodically thereafter, and it helps the equipment establish modulation and FEC coding to use for data transmissions. Now, as we already talked about, the maximum achievable data rates in WIMAX depend on the modulation, the channel bandwidth, and the FEC coding that's being used. Here you can see a summary of some of the data rate combinations that are possible. Now understand that a wider channel bandwidth combined with more complex modulation also means that more data can be sent per signal. Now, as we talked about in Chapter 2, hence the higher data rates that can be achieved with wider channels. Okay. Now, realistic throughput is always lower than the rates that we have here in this example. One reason is that the WIMAX channel bandwidth is shared among the base station and subscriber station, and therefore the number of simultaneous devices actively communicating affects the maximum throughput at any given time. Another reason for lower throughput is that some of the overhead, such as the MAC layer framing, it's not included in the actual rate calculations. The MAC layer WIMAX is typically implemented on a point-to-point or point-to-multipoint basis with one base station and potentially hundreds of subscriber stations, including mobile users. The 802.16 MAC dynamically allocates the bandwidth to individual subscriber stations for the uplink. This is key to the high data rates possible for WIMAX networks. In addition to supporting a large number of subscriber stations, the MAC convergence sublayers allow WIMAX to be implemented as an efficient transport in point-to-point systems for the backhaul. Now, the point-to-multipoint WIMAX network usually operates with a central base station that can be equipped with either an omnidirectional or a smart antenna, which is also called an advanced antenna system. The AAS can transmit multiple simultaneous signals in different directions to different stations that fall within the range of each of the antennas. It also helps to maximize the amount of RF energy sent in one direction. WIMAX can also take advantage of multiple in and multiple out, or MIMO, and reduces the interference of other systems and the impact of multipath distortion. To address a burst to a particular subscriber station, the BS uses a 16-bit number called a connection identifier, or a CID, which is used to identify both the device and the connection after it connects to the WIMAX network. Now remember that the WIMAX MAC layer is connection oriented. Okay, remember in the OSI reference model, connection orientation occurs at the transport layer. Here we're all the way down at the MAC layer. Each station also has a 48-bit MAC address, which is only used during connection establishment. Now, when the stations receive a transmission from the BS, they check the CID and keep only the MAC frames that contain data addressed to them. Stations can then request additional dedicated bandwidth for quality of service if it's required to support a particular service, as the transmission or telephone call or video stream needs. The base station polls the subscriber stations periodically to identify their bandwidth needs, granting bandwidth as required. Jitter is the maximum delay variation between two connection packets over a period of time. Web browsing, transmitting email messages, and downloading files are pretty latency tolerant and jitter tolerant activities. Video and voice, on the other hand, can tolerate a certain amount of errors, but not latency or jitter. Video streams tolerate the loss of image frames, so long as the user still sees at least 15 images per second. However, voice streams do not tolerate losses or delays greater than 50 milliseconds, which seriously degrade the quality of a call to the human ear. The WiFAX MAX protocol maintains a consistent bandwidth by using a self-correcting mechanism for granting more bandwidth to the subscriber stations. Instead, if an SS does not receive the bandwidth grant, or the BS does not receive the request, the SS will simply request it again. The requests from the SSs are cumulative, but they will also periodically inform the BS of a total bandwidth needs. This method is much more efficient than those used by other networking standards, which makes WIMAX a more elegantly designed technology in use for our wireless MANs. A MAC frame includes a fixed length header, and an optional and variable length payload, their data, and an optional CRC, or cyclic redundancy check. The header-only MAC frames are used to send commands and requests between the BS, the base station, and the SS, the subscriber station. The generic MAC frame format is shown here. Next thing we want to discuss will be our security. As with other types of network, security in wireless MANs is always going to be a major concern, because the FSO, microwave security for wireless MAN installations, use proprietary technology. Most of what we're going to be talking about focuses on security measures strictly for WIMAX. For FSO, despite using multiple beam technology, which could allow an attacker to attempt to capture information by interrupting a signal beam, FSO systems are generally considered secure. Anyone trying to sniff information from an FSO would have difficulty accessing the equipment and blocking only a portion of the invisible beam. In addition, such interference would affect the performance of the network, immediately alerting the user or the operator that something's up. For microwave security, each vendor implements its own security protocols. Now, because of the technology being proprietary, but we have 128-bit and 256-bit AES is typically going to be the norm. Using AES encryption means that systems meet not only the minimum security requirements established by the U.S., but also the requirements of privacy laws. Now, as we learned earlier, on the WIMAX protocol stack, the MAC layer includes a privacy sublayer. Now, unlike 802.11 and Bluetooth, the WIMAX standard was initially designed to include very powerful security measures. These features make it extremely difficult, if not impossible, for would-be hackers to steal information from a WIMAX system. The privacy sublayer provides a client-server authentication and key management protocol, with the BS controlling the distribution of the security keys to the SSs. In addition, the standard encrypts all the data transmitted between the BS and the SSs and makes use of digital certificates, which are messages digitally signed by a certificate authority. Manufacturers install a unique digital certificate that includes a serial number in every device. The digital certificate can then be verified with the manufacturer as being valid and unique by sending a copy of the certificate encrypted with the manufacturer's public key over the internet. So you would have to have an internet connection, which is a requirement of the 802.16 standard. The privacy sublayer has two protocol components: the encapsulation protocol and the privacy key management protocol. The encapsulation protocol is used for encrypting packet data and includes a set of cryptographic suites. It is used to apply encryption to the transmitted data. The privacy key management protocol is used for securing the key distribution from the BS to the SSs, and is used for synchronizing the security keys between the BS and the SS. Now, once a device is authenticated with the BS using the digital certificate, a traffic encryption key, which is the security key used to encrypt the data, is exchanged between the BS and the SS for each service connection that's being carried over the wireless interface. Now remember that the 802.16 MAC is connection-oriented and can carry multiple types of service. The TEKs expire, and the SS must periodically renew the keys with the BS. The default TEK lifetime is 12 hours. The minimum value is 30 minutes, and the maximum value is 7 days. Now, only the headers are not encrypted in WIMAX. So to allow the SSs to associate with the network, we don't want to encrypt that MAC address. Now, all data sent across the wireless medium is encrypted using one of the following algorithms. It's going to use either 3DES, where the data is encrypted 3 times with a 128-bit key using the US DES standard. Or it's going to use the RSA with a 1024-bit key. The RSA was developed in 1977 by Ron Rivest, the Adi Shamir, and Leonard Alderman. The algorithm uses a large integer composed of smaller numbers that are multiplied by each other. It is based on the idea that it will be difficult to figure out each of the smaller numbers that are used to arrive to the larger integer. And also AES encryption, developed by the National Institute of Standards and Technology to replace DES. It's still considered unbreakable and is used to protect all unclassified U.S. government material. Today, AES encryption has practically replaced all others, including RSA and 3DES. That concludes our chapter, our lesson on WIMAX. Hope you found it as interesting as I do. And I'll see you back here for Chapter 10, which will be the next progression here, which will be going from metropolitan area networks to wireless wide area networks. I'll see you then.